Chapter 26 is magnetism. So here is the summary of the whole chapter, the big picture. A magnet has a north and south pole. So every bar magnet has a north and south pole. Like poles repel and unlike poles attract. The unit of the magnetic field is Tesla. Electric currents produce magnetic fields. A magnetic field exerts a force on an electric current. A magnetic field exerts a force on a moving charge given by this equation. The magnitude of the magnetic field of a long straight current carrying wire is given by this equation. Parallel currents attract, anti-parallel currents repel. Magnetic field inside a solenoid is given by this expression. Learning objectives. After studying the material of chapter 26, every student should be able to 1. Draw the magnetic field pattern produced by iron filings sprinkled on a paper placed over different arrangements of bar magnets. So basically every student should be able to draw or visualize the magnetic field of a bar magnet and different arrangements of bar magnets. Objective number 2. Every student should be able to determine the magnitude of the magnetic field produced by both a long straight current carrying wire and a current loop. Number 3. After completing the material of this chapter, students will be able to use the right-hand rule to determine the direction of the magnetic field produced by the current. Number 4, students will be able to state the conventions adopted to represent the direction of a magnetic field, the current in a current carrying wire, and the direction of motion of a charged particle moving through a magnetic field. And 5, students will be able to apply the right-hand rule to determine the direction of the force on either a charged particle traveling through a magnetic field or a current carrying wire placed in a magnetic field. Poles of the same kind repel each other. So that means a south pole will repel another south pole, and likewise a north pole will repel another north pole. A south pole will be attracted to a north pole. Magnetic poles always exist in pairs. That means it's impossible to isolate a north pole or a south pole. Consequently, if you cut a magnet into half, as shown, what results is a new north and south pole. So cutting a magnet into half results into two smaller magnets, and no matter how many times you cut the magnet into small pieces, smaller magnets result. So magnetic fields can be visualized by using magnetic field lines. So magnetic field lines are always closed loops. So if you sprinkled iron filings around a bar magnet, you would obtain the pattern shown in figure A. And if you place a compass at different points, the orientation of the compass needle will give you the pattern given in figure B. So basically, magnetic field lines originate from the north and terminate in the south. So magnetic field lines go from north to south. So out of north into the south. The Earth's magnetic field. So the Earth's magnetic field is similar to that of a bar magnet. The magnetic field of the Earth behaves as though a giant bar magnet was buried inside the Earth. Now, when you place a compass inside the Earth's magnetic field, based on the fact that poles of the same kind repel, and poles of the opposite kind attract, so when you place a compass in the magnetic field of the Earth, the north pole of the compass will line up with the south pole of the Earth's magnetic field. So basically what you call north, according to the compass, is actually the south magnetic pole. And what you call south is actually the north magnetic pole, because the north pole of the compass is attracted to the south pole of the Earth. So that gives rise to the terminology north geographic pole, referring to the direction given by the compass, which actually corresponds to the south magnetic pole. And we have the south geographic pole, which is the south of the compass, corresponding to the north magnetic pole. Now, experiment shows that electric currents produce a magnetic field, and the direction of this magnetic field is given by the first right-hand rule, which is shown in figure B. So basically you place your thumb in the direction of the current, and then you curl your fingers around the wire, and that gives you the direction of the magnetic field. So in this case, with the current going up, you would say that the magnetic field is oriented in this direction. To simplify this process, if you can visualize yourself wrapping your fingers around this wire, your fingers will need to go in, denoted by an X on this side, and then out, denoted by a dot on the side. So you would say the field is in to the right and the field is out to the left. Now for a current going this way, the field will be in, below, and out, above. For current this way, the field will be in, here, and out. Now for a current loop, you apply the right hand rule similarly. So place your thumb, hold the loop with your thumb pointing in the direction of the current. So this is your thumb in the direction of the current, and then your fingers will wrap around the loop in the direction of the magnetic field. So in this case, you will say the magnetic field is in this direction. Now if the loop was like this and current was this way, then the magnetic field will be oriented into the plane of the page. And if the current was in this direction, then the magnetic field will be out of the page. Now the second right hand rule involves predicting the direction of the force on a current carrying conductor or the direction of force on a moving charge. So basically you place your thumb, your straight fingers in the direction of the current, and then you bend your fingers in the direction of the field, and then your thumb gives the direction of the force. So like in this case, in the case of A, the current is this way, so you place your fingers, straight fingers in this direction, and then bend your fingers in the direction of the field, which goes from north to south, and your thumb will be pointing down, indicating that the force is down. In the second case, current is coming this way, so you place your fingers in the direction of I, and then bend your fingers in the direction of the magnetic field, and your thumb will be pointing up, indicating that the force is up. Now the magnitude of the force is given by this equation, I L B sine of theta, where theta is the angle between the conductor and the magnetic field. The unit of magnetic field represented by the B is the Tesla, and the symbol is T. 1 Tesla equals 1 Newton per ampere meter. Another commonly used unit for the magnetic field is the Gauss, and 1 Gauss is equal to 10 to the minus 4 Teslas. Now the force on a moving charge in a magnetic field. The magnitude is given by this equation, and the direction again is given by the right hand rule. So this time you place your straight fingers in the direction of V, the direction in which the charge is moving, and then you bend your fingers in the direction of the magnetic field, and then your thumb will give you the direction of the force. So illustrated in this figure, the positive charge comes in this way. Bend your fingers to the south, so direction of magnetic field, and then your thumb is up, indicating that the force is up. Now if the charge is negative, then the direction of the force will be opposite the direction of your thumb, which is down in this case. So take note for negative charge, reverse the direction of your thumb to obtain the direction of force. Now, if a charged particle is moving perpendicular to a magnetic field, so in this case the field is into the plane of the page, and if this particle is moving perpendicular to the field, then by the right hand rule the force will always be perpendicular to the direction of motion, which will result in the particle moving in a circle, because at every point the magnetic force will provide a centripetal force, which is the necessary condition for an object to move in a circle. QVB sine of theta equals mv squared over r. So this is the magnetic force, and this is the centripetal force. And since V is perpendicular to B, sine of theta equals 1. So you end up with QVB equals mv squared over r, and you can solve or simplify this to get the radius as mv divided by q times b. So this is the radius of a particle traveling a uniform magnetic field B with a velocity v. And so here's a summary of the 3 right-hand rules. Right-hand rule number 1 is used to determine the direction of the magnetic field produced by a current in the wire. So place your straight fingers, your thumb in the direction of the current, wrap your fingers around the wire, and the direction in which your fingers curl is the direction of the magnetic field. Right hand rule number 2, straight fingers in the direction of the current, then bend the fingers along B, and your thumb points in the direction of the force. And then right hand rule number 3, which is actually like right hand rule number 2b, for a current, for a charge that is moving in the magnetic field, you place your straight fingers in the direction of the motion of the charge, bend your fingers in the direction of the field, and then your thumb is in the direction of the force. And always remember, for negative charge, the force is opposite the direction given by your thumb. Okay, for a long straight wire, the magnetic field B at the distance r from the wire is equal to mu naught I, which is the current in the wire, divided by 2 pi r. Mu naught is a constant that will be given to you. I is the current in the wire. Pi is a constant, and then r is the distance from the wire to the field point. And of course, the direction is given by the first right hand rule, where you place your thumb in the direction of the current and then wrap your fingers around the conductor to give you the direction of the field. In this case, the field to the right will be in, and the field to the left will be out. Now let's look at the force between two parallel wires. So given two parallel wires carrying currents I1 and I2 in the same direction, so the field of current number 1 at the location of current number 2 will be given by this expression: mu naught times I1 divided by 2 pi times d, where d is the distance of I1 to I2. Now, take note that the field from I1 will be in at the location of I2 and out on the left of I1, because I1 goes this way. If you place your thumb straight up and then wrap your fingers around this wire, your fingers will go in on this side and out this side. Now, using the information that B1 is in at the location of I2 and I2 is up, if we apply the second right hand rule, that means place your straight fingers up since I2 is going up, and then bend your fingers in since B1 is going in, you'll notice that your thumb points to the left, which means the force on current number 2 due to the field from current number 1 is attractive. So based on that, conclude that when two currents go in the same direction, there's an attractive force between them, and similarly when two currents go in opposite direction, there is repulsion. So parallel currents attract, anti-parallel currents repel. Like currents attract, unlike currents repel. And finally, let's look at the solenoid. A solenoid is simply a device that constitutes of coils of wire wrapped around a magnetic material. And solenoids are very important because solenoids produce very strong, concentrated, and constant fields inside the device. The field of a solenoid is given by this equation. Mu naught is a constant, 4 pi times 10 to the minus 7. N is the number of turns, that's the number of times the wire is wrapped around the magnetic material. I is the current, and L is the length of the solenoid. Now it's common to see this equation in this form: mu naught N times I, where small n equals big N divided by L. So this, if you see the equation written like this, is the same, basically the same equation. So again, the summary: magnets have north and south poles, which always occur in pairs. It's impossible to isolate a north pole from a south pole. If you break a magnet into smaller pieces, then smaller magnets resolve. Like poles repel, unlike poles attract. The unit of the magnetic field is the Tesla. electric currents produce magnetic fields, and magnetic fields exert forces on electric current or moving charges given by this. The magnetic field exerts a force on a moving charge given by this equation, and the magnitude of a magnetic field of a long straight current carrying wire, the distance r from the wire, is given by this expression. And parallel currents attract, anti-parallel currents repel. The magnetic field of a solenoid is given by this expression. So that concludes chapter 30. Email me if you have any questions, and my email is m&tam@mytu.sku.edu. Feel free to stop by my office in Chappie James during office hours, of course, or outside office hours by appointment.